for 4 years in the Department of Computer Science and Engineering at IIIT DM Kanchipuram. He has spent 5 years of cumulative industrial research experience. He has 5 years of cumulative industrial research experience with Samsung Research Institute, Delhi, Siemens Technology and Services Private Limited, Bangalore. His research interests include machine learning, computer vision, and autonomous robotics and visual surveillance. His publications comprise international journals and conferences, patents in these domains. He has also served as a reviewer of many peer-reviewed journals and conferences. With this, now I request Dr. Ram to kindly start the session.
Yeah. So thank you, Dr. Deepak, for such a nice introduction and inviting me for this talk. Okay. So without wasting any time, let me start today's topic, that is on recurrent neural networks. Yeah. So am I audible to the participants? Okay. So the participants have joined, right, Dr. Deepak?
Yes.
Okay. Okay. So fine. So in this lecture, we are going to discuss about recurrent neural networks, and then we will move towards a special kind of recurrent neural networks that is known as the long short-term memory or LSTMs, right? So in this, we will see how actually neural networks can make sense of sequential data. See, till now, what you would have discussed, that I think by seeing the whole roster, what I have seen is that till now you have already been introduced to neural networks and then convolutional networks, where how you can process the images and everything, right? But now we will see if there is some sequenced data, like let's say if you are talking about videos. So there would be videos like in sequences, there would be frames in sequences. So how to process that data, or let's say in general, when you get some textual data where you get in sequences, right? So on those kind of data, when the data is in sequence, then how can we process that? And those kind of neural networks where we can actually process these kind of sequences are known as recurrent neural networks. We will see some of the applications, okay? And according to the time, I will adjust like how much I can cover towards the end, right? So many real world applications require actually processing the sequence data. Mainly three types of tasks that we can think of. Like first task is the sequence classification, where one sequence is given to you. For the simplicity, you just think about a textual sequence. Okay, then we will see how we can actually extend to the videos and other things. But let's say a sequence is given to you, and from that sequence, you actually try to classify what kind of data it is. Like for example, you want to do sentiment analysis, or you think about some social media post there where you have some sentence, and from that sentence you want to know what kind of sentiment it is, right? So now you know that how we can do different types of machine learning tasks like classification and regression and all. So the sentiment analysis in test is a classification task where you want to classify like what is the text, if you predict it, to which class does it belong to. Let's say you want to know whether it's a positive sentiment, or let's say we are talking just about two classes, whether it's a positive sentiment and or a negative sentiment. Okay, we can add more classes also. Okay, so that is what is known as the sentiment analysis. Or even let's say if you are talking about videos, right? So we can do activity recognition, like what kind of activity is going on. We can put 5 or 6 activities and we can find out what kind of activity is going on. There also in videos you get sequence of frames, right? So that is also a sequence classification. Or even DNA sequencing. Let's say from the DNA you want to know what kind of genetic disorder is there, right? So that can be one of the sequence classification tasks we can do. Then the other task that you can do is the sequence synthesis. Like from some random data you want to generate some actually meaningful data. Okay, that is what you mean by sequence synthesis. Okay, so like we can do text synthesis, music synthesis, even video synthesis. Okay, from some random data, how we can generate some actually meaningful sequence, whether it is text or music or motion, doesn't matter. Then by combining these two tasks, actually what we can do is the sequence to sequence translation, where a sequence you just think, for the simplicity as I told you, just think about a textual sequence or textual sentence, and from there on how we can generate actually another sentence, like we are doing currently in this GPT. You put some sentence, then from there on it will actually generate a new sentence for you. Right, so that is what is sequence to sequence translation. So it is like a combination of both classification and synthesis, right? So here what we are going to do is that speech recognition. Like let's say from some speech you are giving in audio form, and you want to generate that the corresponding textual sentence. Okay, so that is what is speech recognition. Then text translation also, you want to translate from one language to the other language, that can also be done. Even part of speech tagging, right? Some part of the speech you want to like tag, like this this part of the text is giving this emotion, the other part is giving this emotion. Okay, so if you want to generate that kind of sequence, that also can be done. Okay, so in general, when you are thinking about like sequence structures, these are the three tasks that we can do: sequence classification, synthesis, and sequence to sequence translation. Okay, so in this talk we are going to discuss how we can actually achieve these three tasks with the help of neural networks, or in general this recurrent neural networks. Okay, so now we'll describe this more formally. Let's say given a set X, if Sx denotes the set of sequences of elements of X. Okay, so if you are thinking about English language, let's say, so this X will actually be the set of all the words that can be possible in the English dictionary. Okay, and then the S of X actually will be the all the kind of sentences that you can actually generate from the words that are given in the set X. Okay, so formally if you define, or mathematically if you define the S of X, or the sequence, you can think of like the sequence set of X is defined as the union of all the power sets of X, right? So power sets of X means, let's say you have 5 words in this set X. Then what we are talking about is we are generating sequences of length 1, then length 2, all the possible sequences of length 1, length 2, length 3, length 5, like that. Okay, so that's why you can see it is the summation of the power sets of the sequence of power set of the X, right? So it will generate all the sequences of length 1, 2, 3, like that up to infinity. Okay, so if you are talking about English dictionary, then it will generate all the sentences that can be possible in English by using the English words. Okay, so now then we formally can define all the three tasks that we have discussed in the last slide, like sequence classification, where we want to generate a model F, where the input will be one of the sequences from this sequence set. Okay, so one of the sentences or sequences that you will take from the sequence set, and it will generate a to which class does it belong to, right? So one of the classes. Okay, so it will generate one of the classes to which it belongs to, like you discussed about the tweet classification, right? Whether it's positive sentiment or negative sentiment, like that, right? So that would be the sequence classification task, where you take one of the inputs from the sequence set, and then you try to find out to which class does it belong to, or you try to predict which class does it belong to. In case of sequence synthesis, as I told you, it takes actually the random data to generate a meaningful sequence, right? So you see, you are taking some d-dimensional data, right, having d number of features, some random feature set, and from there on you try to find out a meaningful sequence from your sequence set that you have taken, right? So that is the sequence synthesis. That means you are generating a new sequence out of nothing. Okay, so that's why it is known as sequence synthesis. Then sequence to sequence translation, again you are generating a function where you take one of the inputs from your sequence set. Okay, let's say you are talking about English dictionary, then you are taking one of these sentences that is made out of English words, and then again you try to generate some sentence either from the same set or from some other set. Like in this case, you see Sx to Sy. That means you can take some sentence from the some sentence made out of English words, and you can generate also a sentence that is made out of, let's say, Japanese words, right? So that in that case, this Y will be the set of all the words in the Japanese dictionary. Right, so that's why sequence to sequence synthesis, we can have like from same sequence set to the same sequence set, or from same sequence set to some other sequence set also. That is also possible. So these are the three main tasks that actually we can do with the sequence when sequential data is available to us, right? So in the for simplicity, in this case I'm just using textual data as an reference, but you can always extend it to videos and all, where you have multiple frames in the sequences, and similar you can just try to find out what would be the mapping, right? So in the rest of the slide, we consider only time index signal, although it generalizes to arbitrary sequences. Time index means we are saying that if there is a word, there is like 5 words, we'll say that the first word is at time sequence 1, second word is at time stamp, or you can use the word stamp. So first word is in timestamp 1, second word is in timestamp 2. That means we are thinking that at each timestamp we are getting 111, right? So that we will actually represent by the letter T, right? So with this small introduction, like what would be the input to the neural network, we are going to discuss how recurrent neural networks are actually going to help us in achieving those tasks, like sequence classification, sequence synthesis, or sequence to sequence generation. So when the input is a sequence, okay, now we will go more formally, like how a computer can actually understand. So when the input is a sequence, let's say X belongs to SRP. So you see, if you go to SRP, S X is nothing but it is the set of all the sequences that can be generated from the words in X. So if you just extend it, so you see SRP means it is the sequence of, or you can think of like it is the set of all the sequences that can be generated by using a words of length RP, or length of size, or you can think of like a vector, because now you are representing in RP means Euclidean domain, we are representing RP, right? So you are representing as p dimensional vector. So if each word, let's say you are thinking about English dictionary, if each word in your English dictionary can be represented by a p dimensional vector, then this SRP represents all the sequences that can be made out of the English dictionary, right? So this SRP, in that case, each word you are representing is a p dimensional vector. Okay, so let's say you are talking about some sentence like a quick brown fox, right? Something like that. So in that case, that A will be also represented by a p-dimensional vector, a quick will be represented by a p-dimensional vector, then the brown will be represented by a p-dimensional vector, like that, right? So that's what we are saying. When an input sequence X, that means you are taking one sequence out of that sequence set where every word is represented as a p-dimensional vector, right? So then the input sequence X belongs to SRP of a variable of length Tx. We are saying that the length can be variable. It can be of length 1, length 2, length up to Tx, let's say. The historical approach is to use the recurrent model, which maintains a recurrent state Ht belongs to Rq updated at time step T. That means at every time step, what we are going to do, we are going to take the input at that teeth time space, teeth timestamp, and we are going to maintain a recurrent state, right? So in historically, in recurrent neural networks, why we are telling historically? Because nowadays there are other kinds of neural networks like this transformers and everything, which are like better versions of this recurrent neural network. So historically, we were using this recurrent neural networks actually to generate a recurrent state Ht belongs to Rq. So what we are doing, see every time stamp. So if you are thinking about, like I gave an example, a quick brown fox. So A will be represented by a p-dimensional vector. The quick will be represented by a p-dimensional vector, brown will be represented by a p-dimensional vector, and fox will be represented by a p-dimensional vector. So that means at every time step, so if you are thinking the first t equal to 1, you are getting a, t equal to 2, you are getting quick, t equal to 3, you are getting, let's say, brown, right? So every timestamp you are getting a p-dimensional vector to you. Now that p-dimensional vector will be taken as an input along with the previous output to actually generate a recurrent state Ht, which will actually belong to Rq. That means you are generating a q-dimensional vector. So from a p-dimensional vector, actually you are generating a q-dimensional vector. So that is how the recurrent neural network goes. Okay, so I think it will be better explained when I show with a diagram. Okay, I will come to that in one more slide. So formally for t equal to 1 to tx, because your length of the sequence is tx. So formally for t equal to 1 to tx, you define your recurrent state Ht. That means the output of the recurrent state Ht is as a function which takes the input xt. That means the current input or the current word from the sequence, right? That is xt, and then also the previous recurrent state output. Okay, so that ht minus 1, that is where you maintain the state. So what you are taking, you are taking the output from the previous state as well as the input from this state, right? So both with parameterized over a parameter vector theta, right? So this function can be arbitrarily very complex, or it can be a very simple also. Okay, we are not talking about this function, we will come to this later on. So we are just thinking about, we are trying to generate a function which will take the input at this timestamp and the output from the previous timestamp, right? And that will be parameterized over some parameters, let's say theta, right? So you see what you are doing. So this phi function, if you see, it is from Rp to Rq, because you see your input, as I told you, the input word at a time stamp t is represented by a p-dimensional vector. So that is Rp. Then, as I told you, your recurrent state is represented by Rq. That means at every timestamp, whatever the output will be, let's say ht or ht minus 1, or in general h0, h1, h2, everyone will be represented by a q-dimensional vector. So that's why you see your function is from Rp cross Rq to Rq. That means again it will generate ht, the output or the recurrent state output for this timestamp, right? So that will be represented by Rq. Then again at the beginning, of course, you have to take some random h0, right? Again, there are different ways to initialize it, but again, you have to take some input because that will be the input for your first file, right? Where your x1 will be the input and h0 will be also an input that will be parameterized over theta, right? Then once you do that, so you can think of, I will show you the diagram, then you just remember or just try to follow what I am saying over here. Then what we can do in the next slide, you can actually connect it with the circuit diagram, or you can think of the network diagram, and then you can actually understand the whole concept, right? So then the predictions can be computed at any timestamp t from the recurrent state by giving yt equal to, there is another function we are using, let's say psi, which takes the last, you see ht, that means the, you can not the last, you can think of like at any timestamp, whatever the output that you are getting, right, or the recurrent output that you are getting, that will be taken as an input now, okay, and that will again be parameterized over the theta, right? Or we can think of like theta is the parameter vector which contains all the parameters of this model phi as well as the model psi, right? So the predictions can be computed at any timestamp t, not only at the end but any timestamp t from the recurrent state, okay? So from that current recurrent state, let's say you are talking about the timestamp t, so from that timestamp t we can take the output of the, or the recurrent state output of that timestamp, okay, and we can generate it, or we can think of a new function psi which will take that input, which will be parameterized over theta to give you the last output, let's say yt, right? So you see that now your psi function, which is like taking an input from the the current the recurrent state output, which is of dimension q, so that's why it's a function defined from rq to rc, because you are going to get one of the classes. So this yt should belong, it's yt, you can think of like a probability score, right? It will give you probability score for, let's say you are having 3 classes, so it will give one probability score for your class 1, other for class 2, other for class 3. So it is, you see, it is giving 3 values, right? So 3 values again, that can take any real number, right? But if you're thinking about probability, of course it will be in the range of 0 to 1, but in general, if you are thinking about any score before actually converting to probability, because classifiers can be score classifiers or probability classifiers, if you're thinking about a score, it can actually give you any real value in the domain of minus infinity to plus infinity. That's why you can take real value r, and it can give you c number of real values, because it depends on the number of classes. If you have c number of classes, then it will generate c number of scores for you, right? So that's why you see the psi function is defined from rq to rc. Now if you remember this phi and psi, then your whole job is done, because now we just need to connect it with the network diagram of the recurrent node, right? So let us see for one unit. Let's say we'll start from one unit, then we'll try to extend how it actually goes. So you think so if you see this phi function, what does it take? It takes the current state input, right? Current timestamp input xt, which is of p dimension, and it also takes the output from the previous recurrent state, that is ht minus 1, which is of size q, right? So if you are thinking about the first stage, so you see x1, you are this phi function, it takes an input x1, that is the timestamp 1 input, which is a p dimensional vector. Then it also takes the output from the previous state, so h0 initialized with some random value, right? So which is a q dimensional vector, right? So this phi function takes the input h0 as well as x1, and this is parameterized. So this is red circle is parameterized, right? On which parameter does this function actually depend on, right? So it is parameterized over theta to actually give you a recurrent state output h1. Okay, so that is for the first input. Let's say you are talking about a quick brown fox. It's this example I am giving. So that quick or a, we can think of the first word a, which is represented as a p dimensional vector. Again, there are different methods to actually represent them in vectors, right? So that I am not going into. That is for the coding part. So when you are thinking about a p dimensional vector, so it can there are different embeddings for that. So this a will be represented as a p dimensional vector, and that will be taken as input. Then this h0 with a default value will be taken as an input to your function. I'm just representing this as a function. Okay, I have not told that it's a neural network or something. Okay, we are just talking about functions, right? So let's say a function, we are passing it to a function which takes the input h0 and this x1 with parameterized over theta. Okay, this is not an input, this is the parameter. Again, this, as I told you, these red circles are the parameters. So this is parameterized over theta to give you an output of h1. Now in the next state, what will happen? This x2 will be an input. Now this h1 will also be an input to the next stage. Okay, again parameterized over the same theta. So you see this will go on. So for the second state, what will happen? You see the second word like a quick. So quick will be represented as a p-dimensional vector that will be taken as an input to this phi function. Also this h1 will be taken as an input to the phi function, right? Then it will be parameterized over the same theta, right? And we can go on till the last last word in that sequence, or the last timestamp word, right? So you see every step we are generating a recurrent state output h1, h2, up to ht. And the most important thing over here is that you see we are using the same phi function. Okay, so that's the most important thing over here. Now coming to this phi function, what could it be? Okay, so it could be a very simple function, like you can just think about a simple, very simple neuron, like just taking some inputs and with fully connected neural network and all, just one layer neuron. Or it could be a very complex like multi-layer perceptron. It can be anything, right? So from x1, x2, xt to it can generate up to h1 to ht, right? So from a t dimensional input, we are actually sorry, from a t length sequence, we can actually generate a t length sequence where each word or the each output and every timestamp can be represented as a q dimensional vector, because this x1, x2 all can be represented as a p dimensional vector. Now this h1, h2, of course h0 is also there. So h0, h1, h2 can all be represented by a q dimensional vector. Now the, so this is just the recurrent state output. Now the next step is to actually generate, let's say you are doing the classification problem, so we need to actually classify it. So how can this be done? This can be done again in two steps. One could be directly we can take the last stage output, because when you are thinking about the t state, it is dependent on the t minus 1 state. So of course the previous data is also propagating to, or we can think of like forward passing to the last output. So of course you can take the output, the last stage output, that is the ht, right? And we can just pass it through a new function psi. Okay, and you can generate the yt like I told you in the mathematical form. Okay, so it will just take the input ht to give you an output yt, and this psi function again can be parameterized over the same theta. So here all these phi and psi functions, you can take any arbitrary very simple neural network, or you can also take very complex neural networks. Even it's, you can see that there is a concept because of which I told you that here we can use phi and psi, but again you can use the same kind of neural networks in both the cases. That will also work well, not an issue, right? So it depends on you what kind of neural networks you want to take in these places, right? So this is the whole idea behind recurrent neural networks. So just you have to remember that the input to the neural network at any stage uh, is the word at that stage, or the what you can say, the coding of the or encoding of that word at that state plus the output from the previous stage. So if you remember that, then recurrent neural network is half done. Then you have just to have to realize through the neural network concept. So, or you can think of like this, the neural network diagram. So in this case, I think it is much more clear. So then let's say you want to actually, instead of, so in this case, if you see in this diagram, we are just using the output from the last stage to actually get the output yt. Even you can, what you can do, you can extend it to take the output from every timestamp. So you can think of like we can take the output from h1, we can take the output from h2 up to ht, and similarly we can generate y1, y2, yt. Like we were just generating the last output yt because of a classification. We wanted to do a classification, that's why we needed only one output, right? So that's why this one output can be a probability. When I say one output, again, this is not just one output, it is like a vector of what do you say, c values, because you have c number of classes. So for each class it will have one probability value associated to that, or a score value associated to that, right? Now if you actually extend it to sequence to sequence, so that means you are taking one sequence as an input and want to generate another sequence. So what you can do, for every state output, right, or every timestamp output, you can generate the corresponding what do you say, corresponding output, right? So you see for x1 you can get y1, for x2 y2, for xt you can generate y2 yt. That means from a t length sequence actually you can generate a t length output. Okay, so that is where we actually use sequence to sequence generation. So even though the number of steps t depends on x, because as I told you, this the t, the how many timestamps would be there actually depends upon what is the sequence length, right? So this t is dependent on the sequence length. So even though the number of steps t depends on the sequence, depends on x, this is standard computational graph. Okay, so those who are thinking like, let's say my t is equal to 2, so whole of this diagram will stay in this part of the neural network, right? But if let's say t equal to 10 or 15, then it is keeping on, then it will keep on increasing, right? So even though the number of steps t depends on t, this is a standard computational graph, and automatic differentiation can deal with it as usual. Because when you are thinking about, let's say, creating that neural network in a coding environment, what you are going to do is that you are going to use a loop, right? So your loop, let's say, is length of you are taking length 2, then the loop will run for 2 iterations and it will create that part of the neural network. Let's say this part of the neural network it will create. Let's say your length is 10, then that loop will run for 10 times, and similarly it will create the whole neural network from, right? So depending upon your length of the sequence, it will generate that neural network for you, and then it is like standard back propagation, whatever you have learned in neural network. So nothing is going to change. So many people get this idea, right? We are getting dynamic length inputs, so how can the neural network can handle? Because the neural network can handle because you are generating the neural network based on the length of the sequence, right? So automatically back propagation or the automatic differentiation is going to handle that part of the task. So in case of recurrent neural network, this is actually this kind of back propagation or automatic differentiation is known as back propagation through time, because you have time domain sequences. So this is how the back propagation moves. So let's say you have the output yt. Now because with this yt, you will have some ground truth data also, right? So that ground truth data and this yt will actually generate a loss for you. Now that loss needs to be differentiated, right? If you remember your gradient descent formula, which says that wt plus 1 equal to wt, or theta, we can use theta, right? Because parameters is a vector. So theta t plus 1 equal to theta t minus eta multiplied by del L by del theta. So if you see that for finding out the del L by del theta, right? So your loss is over here and the parameter theta vector is over here. Now this can be propagated and we can use the chain rule of differentiation to actually get del L by del theta for each of these entities that are there, right? So automatic differentiation is not going to be difficult. Now with this, again, we will move to a very simple recurrent neural network, which is known as Elman networks. Okay, so Elman networks is like a very vanilla mode of RNN. You can think of like very simplest model of recurrent neural networks. So Elman network consists of phi and psi defined. So you see now we have two functions: phi, which is for the generating the hidden state. We can, because this H actually represent the hidden states. Okay, we can tell that as recurrent states also. So there are two functions now, this phi and this psi, right? So this phi function is actually, you can think of like Elman networks consists of phi and psi defined as primitive neuron units, very simple neuron units actually, right? Such as logistic regression units. Let's say I hope everyone knows about logistic regression, which is very simple, which is actually takes the what you can say linear combination of the inputs along with the sigmoid activation. Okay, sigmoid activation, then the linear combination of the inputs. Okay, so that is what is logistic regression unit is. So this Elman network consists of this phi function and psi function defined as primitive neural units, such as logistic regression units, or you can think of like HT is equal to, you see, linear, as I told you, linear combination of the inputs, right? So that means you have xt, you have ht minus 1, then the xt is weighted over some weight matrix, let's say double xh. Okay, so let's say xt is of size, you can think of like xt is of size, as I already told you, is of dimension p, right? So xt is a p dimensional vector. When I say xt means it's the word at the teeth iteration, right? Or not the teeth iteration, but the teeth timestamp, right? So the word is represented by a p dimensional vector. So now you are multiplying it with a weight matrix of double xh. Okay, so that means it's a matrix of size. You see, you have a p dimensional vector, so the something needs to be multiplied, so that means you need to have a weight matrix of size something multiplied by p, because you are having a p dimensional vector. Okay, and you want to generate a q dimensional vector because ht is a q dimensional vector, right? So that means this matrix double xh transpose would be of size q cross p. Okay, so this would be of size q cross p, this would be of size p cross 1, so it will generate a q cross 1 vector for you, right? So this WXH actually will, or you can think of like double XH transpose will be of size Q cross P. Okay, so this is wrong actually. You can just, those who are writing, they can just write double XH belongs to RPQ. So that double XH transpose will actually belong to Q cross P. Right, so double XH will transpose will belong to Q cross P. Then you are multiplying with a P cross 1 vectors, which will generate a Q cross 1 vector. Right, then again for the second part, HT minus 1, again as I told you, linear combination. So again a weight matrix will come into picture, and that for that there is no issue because you have a Q dimensional vector Q cross 1. So you need to multiply with a Q cross Q, then with Q cross 1. So your WHH will be of size Q cross Q. So Q cross Q multiplied by Q cross 1 will actually generate a Q cross 1 vector, and this BH will be the bias part where you again will take Q cross 1 vector. So you see, this is the whole of this is Q cross 1, then this is Q cross 1, then this is Q cross 1. Then the linear combination will be passed through the sigmoid activation function to generate a Q cross 1 vector for it. Right, so this is just a very simple, you see, we are not taking very in this Elman networks, we are not taking actually very complicated neural network, just a very simple neural network, which is the linear combination of the inputs. Okay, when I say inputs in this case is the input at that time stamp, that is xt, and the output from the previous, or the recurrent state output from the previous state, that is ht minus 1. So you are going to generate a Q cross 1 vector. Now once that is generated, then you can generate the yt, okay, or the output at every stage, that is yt, which is again is a linear combination of the inputs. So you see, if you see this diagram, the psi function just takes the input h1, okay, or ht in general, or the timestamp t, it takes the input ht in general. So the psi function will be a linear combination of this ht, right? So that's what we have done. You see, yt is a linear combination of this ht. Now will be added with a bias. Okay, so you are now not new to the neural networks now, because you have done so many classes by now. So you are not new to the neural network, so you know what is a bias and all. So you see, this ht will be of size Q cross 1, will be actually multiplied by a vector of 1 cross Q, right? If you, because this yt, as I told you, will give you one value, right? So if you generate one value, that means it will be of size 1, right? So to generate a size of 1, actually you need to multiply this 1. Let's say your ht is Q cross 1, you will actually multiply with 1 cross Q to generate 1 cross 1 vector, right? So, and again this by will again be a single r value or a scalar value, right? So you will generate a scalar value over here by multiplying 1 cross Q with the Q cross 1, and again you will add it with a 1 scalar value, right? So you are going to generate a scalar value, which will again be passed through a sigmoid activation function to generate a value between 0 to 1, right? So at the end, this yt, that every stage output will be a value, right? This y1 will be a value, scalar value, y2 will be a scalar value, yt will be a scalar value, right? So that is how it is done, this Elman networks. Again, for the choice of non-linearity, like we are using the sigmoid activation function, we can use the 10 hyperbolic and the ReLU activation function. But it's you would have learned that when we are using the sigmoid activation function, generally it gives you the problem of vanishing gradients and all. But you are going to see that in case of recurrent neural network, actually we use the sigmoid activation function and 10 hyperbolic activation function. Okay, so if time permits, we will also see why it is not a problem in case of recurrent neural networks to actually use the sigmoid and 10 hyperbolic activation functions. Now let us take an example, okay, and see how the outputs would be. So let's say we want to learn to recognize the variable length sequences that are palindromes. Let's say a variable length sequences are given to you, and we want to know whether that sequence is a palindrome or not, right? So if I hope everyone knows what is a palindrome, because it's very simple. Okay, those who do not know, they can also, I'll just tell for them. So palindrome is a sequence which, like, if you read from the start to start to end, or end to start, they will actually be the same, right? Like we have, let's say, word madam, madam. If you read from the start or the end, it will be actually generate the same word, right? So that is what is a palindrome is. So in this case, what is done here is that for training, we use sequences of random sizes from 1 to 10. Okay, random size. It can be of sequence 1, sequence 2, up to sequence 10, right? Like this first case, 1 2 3 2 1, which is a palindrome, because if you read from this side or this side, they actually generate the same sequence. So it is palindrome. This is also the second example is also a palindrome. The third example is not a palindrome. The fourth example is a palindrome, because one letter is there, so automatically it's a palindrome. 1-4, again, it's not a palindrome. Let's say these kind of sequences are given to a neural network to see or to classify whether that sequence is a palindrome or not. See, for a human being, it's very simple, but how a neural network would do that, that is what is the question. Actually, I have trained it for like 20 epochs by taking the cross entropy loss as a, because for classification, you know, we can use the cross entropy loss for to find out to do the wave propagation or to learn the function f, right? So we have used the cross entropy loss function for 20 epochs, and it is shown that, you see, it is like in 20 epochs it is reaching up to a loss of, we can think of like 0.25, which is still can be decreased, right? But we can see that it's not, it is trying to somehow stabilize, but that's not the case. We can reach up to, in theoretically we can reach actually loss up to 0, right? So this we can think of like a better mode. So now what we can do, we can actually extend the same concept of recurrent neural networks to a new concept called as bidirectional RNNs, or generally we call them as bi-RNNs, right? So what is that then? Computing the recurrent states forward in time does not make use of future inputs x t plus 1 to t, even though they are known. So let's say we are talking about this sequence 1, 2, 3, 2, 1, right? This is a palindrome, right? So as I told you, you need to take input, let's say this 1, okay? You are taking, let's say this is timestamp 1, timestamp 2, timestamp 3, timestamp 4, and 5. So let's say timestamp 1, if you are taking the input 1 as input, right? So you are not actually making use of the inputs like 2, 3, T, 1, even though they are known to us. If it is not known to us, then that is a different thing. But let's say the whole sequence is known to you from the beginning. Okay, you know what is the whole sequence, like in case of a tweet, you know the whole sequence from the beginning, right? If it is a randomly generated or dynamically generated data, then I can understand. But if it's a sentence that is already given to you, or sequence that is already given to you, that means you know the whole sequence. Then the question is, why not use the data that is already available to you? Why not use the words that are actually available to us after that timestamp, right? So that is the actually concept behind bidirectional RNNs. So computing recurrent states forward in time does not make use of future inputs x t plus 1 to 2 t, even though they are known to us. So RNNs can be made bidirectional by consuming the sequence in both directions. So we can consume the sequence from the forward direction as well as backward direction. Exactly same RN, whatever we discussed, just you try to visualize by taking in both the directions, how the inputs can be given from both the directions. So effectively this amounts to run the same, okay, single direction RNN that we have already discussed twice, right? Because once over the original sequence of 1 to t, okay, so you will have a original sequence 1 to t that we discussed for a single stage RNN or single RNN, single direction RNN actually. Then you can think of like once over the reverse sequence. So you can think of like you are giving the words in the reverse sequence from xt to 1. Okay, so that is what is a bidirectional RNN is, when you define the RNNs in forward direction as well as in the backward direction. So the resulting recurrent states of the bidirectional RNNs is the concatenation of the two resultant sequences of the recurrent. This is very important. The third point is that, see, every stage, let's say you are running from x1 to t. So for every timestamp, you are going to generate one output ht. Right? So for xt, you are going to generate ht. Similarly, in the reverse direction also, for xt, you are going to generate another ht. Okay, so that is the resultant recurrent state. So that means but you need only one recurrent state. So now you are generating two recurrent states, one for the forward direction and one for the backward direction for every timestamp. For every timestamp, you are generating actually two recurrent states, one for the forward direction, one for the backward direction. So the resultant recurrent states of the bidirectional RNN is the concatenation of the two resulting sequences. That means if you have, let's say, ht is the output in your teeth timestamp, right? So that is a vector of dimension q. So in the forward direction, you are going to generate a q dimensional vector. In the backward direction, you are going to generate a q dimensional vector, right, for the timestamp t. So what can be done? We can actually concatenate to generate two q vector, right? So ht from the forward direction, ht from the backward direction, concatenated together to actually generate a ht of dimension 2q. So that is what is the concept of bidirectional RNN. Now, by using the bidirectional RNN, actually, theoretically, it should have improved, because we are using the concept like how to use the sequence from this timestamp to the last timestamp, but actually it didn't improve for this application. But having said that, there are many applications where actually this kind of bidirectional RNNs work far better than actually RNNs. Okay, but for this particular kind of data that we have taken, because data is the what is it? Data is actually the king in case of machine learning or deep learning. So if your data that we have generated is not good enough, then of course this kind of models are not going to work. So the data that might have been generated, it doesn't work that well for this bidirectional learning. But what I'm saying that in general, when you have some data where the words after a timestamp is available to you, better to check the bidirectional RNN whether it works well or not. Okay, in most of the cases it is going to work. Okay, but it's the same that it didn't work in this case. Now again, we can actually extend the single direction RNN to a new concept called as stacked RNNs. Okay, so as the name suggests, we can put the RNNs in a stack, right? So stack means one after the other, like a book stack, right? So recurrent networks can be viewed as a layer of producing a sequence H1 to TL. So you see, previously we were just generating H1 to T. That means we are generating the H1, H2, H3 up to HT, right, for each timestamp. Now we can actually extend the same network that we have discussed till now to stack it. Like you can let me go to the diagram once. So you see, this is what we were doing, right? So you can think of like this is one book. Over it, you will put another book. Okay, so if you are thinking about this as a whole book, on that you are going to put another book, then on that you are going to put another book, right? So that will create this stack. So for the next stage, what is going to happen? This y1 y2 up to yt will be actually taken as the timestamp inputs. Like in the previous case, x1 x2 up to xt were taken as the input for the current what do you say, current RNN, right, or the single direction RNN for the current RNN. The similarly y1 y2 yt, right, they can actually be not y1 y2 yt, actually this h0 h1 h2 ht, because this y1 y2 yt actually are the outputs. Okay, so when you are thinking about like that book example I gave, you can think of like the book is up to this, not the final stage, because we don't final stage we need at the last, right, once you put all the books together, right? So this is just one book output. So you can think of like this h0 or h1 h2 up to ht are the outputs from the current RNN. Now this h1 h2 ht you can think of like a sequence, right? Now that sequence can be taken as an input to another RNN. Like we can repeat the same block, right, and we can put it stack together and can continue for some stacks, and you can see what is the output, right? So that is the concept of stacked RNNs. Let us see that. Okay, so you see, from x1 to t we are generating h1 to t, which is again we are using it. So this is the RNN that I discussed over there. So you see, x1 to t is taken as an input, right? So that means for every timestamp you have x1 x2 x3 up to xt, and you are using an RNN to generate h1 h2 up to ht, each of size. So each word of size q dimension. So here each size of p dimension, here it's each of size, let's say q1 dimension, because now you have h1, so you can think of like q1 dimension. Now that will be taken as an input to another RNN, right, like what we discussed in the previous case, to generate h2 1 2t. You can think of like h2 each generated each generated word, each of size, let's say q2, right? So h1 to t2 at the level 2. Similarly, that can be taken as an input for the third level, then the fourth level, up to the nth level, right? So we can actually stack L number of RNNs in a sequential way, and that is what is known as a stacked RNN. So you see, at the end, the psi function comes. Psi function doesn't come in between. Psi function, which is the actually the classifier or the last stage. We can think of like the psi is the last stage function. It can be a classifier, it can be a regressor, whatever, right? So the psi function actually comes at the last, which takes the output from the last RNN layer, which 1 to TL. So nth layer, it takes the input and it generates an YT. Right. So in this case, you can see for every we have used the same RNN or the similar because they are all parameterized over theta. For every stage, you can see for every stage in that stacked RNN or every entity in that stack, we are using the same parameter theta, but that is just a simpler model. We can actually use different RNNs over here. When I say different RNN, means different configuration RNNs you can take over here. Okay, here you can use a simplified version of a neuron, Here you can take two-stage neuron, here you can take a multi-stage neuron, doesn't matter. Okay, so for simplicity I'll just put a parameter theta, but in general it could be theta 1, theta 2, theta 3 up to theta l, right? So that can be done. So this is the concept of stacked RNNs, but when that is put together, still the same task that I was doing could not give me good results, right? So that means maybe for this task it is not working, but in general we are increasing the complexity of the model, we are increasing the number of parameters, because previously you see you would have only one theta vector, now you have n number of theta vectors, so the number of parameters are increasing. So in general we would think that it should give you good results, right? But it is not for this task specifically. Again I am saying, not for other tasks in general. Maybe for some other task with good data it would have given a better result than the normal Elman network or the bidirectional RNN. Okay, so with this we will go to a new concept called as gating, right? Because the intuition behind using this concept of gating is that now we saw that for this application it is not giving good results. So one of the culprits in case of neural networks, when it is not working well, one of the culprits always is the vanishing gradient, right? You would see that okay, we are keeping on increasing the neural network, so of course there is this concept of vanishing gradients, where you keep on increasing the layers, it will just vanish, the gradient is going to vanish towards the initial layers, right? So that could be the one of the reasons that could be happening over here, right? And the same intuition came to the researchers minds when they started the concept of gating. So when unfolded through time, the graph of computation of a recurrent neural network can grow very deep, right? Like we saw in this previous case when you are using stacked RNNs, and training involves dealing with vanishing gradients. Of course, when you keep on increasing using the sigmoid activations and all, even though you use ReLU activation, doesn't matter. You are going to ReLU activation is not a what do you say? It's not a one-stop solution for vanishing gradients. If you keep on increasing, even the ReLU can give you vanishing gradient, but it works better than sigmoid activation. That is the concept that is there, right? So when unfolded through time, the graph computation of a recurrent neural network can grow very deep, and training involves dealing with vanishing gradients, of course. So RNN cells should include a pass through or a additive pass, so that the recurrent state does not go repeatedly through this quasing nonlinearity. That means the gradient is not going to vanish. How we can make sure of that? By including a concept called as pass through, or those who have actually, I think yesterday you did have the convolutional networks, you would have heard about a concept called as ResNet, where they use the skip connection. So this pass through is exactly the same where you use the skip connection, right? So by using a skip connection, actually we can come out of the vanishing gradient to some extent. So that is the concept. So this is identical to skip connection in ResNet neural networks. So you see, previously what we were doing, we were passing ht minus 1. Of course xt is there, xt is always there, so that we have not considered over here. xt is there, so you are giving to a neural network phi, which is a function phi, with the input ht minus 1, then you are getting the output ht. That is what is happening, right? Previously there was no plus, previously there was ht minus 1 going through this phi function along with xt to give you ht. Now that what the researchers have told, that instead of, you can use this phi function to generate the proposal ht bar, let's say. Now, at the same time, what you can do, you can make a direct skip connection and add it to the proposal, right? So here you are going to, let's say, you are going to generate ht bar. Let's say by taking this phi function and ht minus 1 and xt as input to the phi function, you generate ht bar as output. Then you add this ht bar actually with this ht minus 1. So ht bar added with ht minus 1 will give you actually ht. Now you see, while back propagating, right? It will not have just one direction, right? So this, you see, sigmoid activation comes over here, right? So that can generate actually the vanishing gradient problem. So instead of just going in one direction, now what you can do, you can actually, your ht can go in both directions. So those who are familiar with the concept of automatic differentiation and back propagation, they will know that for generating the gradient, you need to go in this direction as well as in this direction, both the directions. So in this direction, you are not going to encounter that much problem, right? So that is where the skip connections actually was a very good invention at that point of time when they proposed this ResNet, right? So this gating is such a concept where actually you try to find a pass through to the previous cell state input, right? So that is what we are going to use in this concept of gating. Okay, so if you generalize it, what will happen? For instance, the recurrent state update can be a per component weighted average of its previous value ht minus 1. Okay, now we are just not going to take directly ht minus 1, rather we are going to take a weighted average, right? So we will give some weightage to, so you see in this case we are giving directly weightage of 1. If you add it like let's say ht bar from here and ht minus 1 over here, so we are getting directly a weightage of 1. So instead of doing that, if you generalize it, what you can do, you can give some weightage to this ht minus 1 and some weightage to the ht bar that is generated from here. So that is the concept of gating actually. So for instance, the recurrent state update can be a per component weightage average of the previous value ht minus 1 and full update ht bar. Okay, with the weighting factor zt depending on the input and the recurrent state, hence acting as a forget gate. Okay, let me explain that. So formally what you can see this ht bar, which is takes an input xt, and so ht bar is the output of this phi function, okay, or a neural network which takes an input xt and ht minus 1. Like in this case it is taking an input ht minus 1, of course xt is over here, and it generates let's say proposal that is not, let's say we say that ht bar, that is not the final output but rather a proposal or rather a tentative value, you can think of like that, it's tentative value. Then we are generating a zt, right? Zt, we are saying that it's a forget gate, and what is that? It is again a function f which takes the input xt and ht minus 1. You see it is taking again the input xt, so that means you are putting a function over here f which is taking the input ht minus 1 as well as xt, like in the previous case, which is parameterized over again over theta. You can think of another neural network, but what will happen is that this f function will be a sigmoid function, so it will generate a value between 0 to 1, right? So it will, what it will happen, so it will, let's say 0 to 1, let's say you are generating a value between 0 to 1, then it will give some weightage, let's say you are generating 0.7, so you will get, it will give 70% weightage to the actually the previous state cell output, sorry, previous stage recurrent output, then it will give 30% because 1 minus zt to the actually the current tentative output, that is the ht bar. Okay, so that means if zt tends to 1, then it will completely bypass the phi function. If ht, let's say if you are generating zt equal to 1, then it will completely use this path, right? If you are completely zt equal to 0, then it will use the actually the proposal path, right? So this zt is going to be learned now, right? So it will actually help us in taking a good decision. That's why it is known as a forget gate. Forget gate, why? Because you see, when it is 0, then it is completely forgetting the previous stage output, right, or previous stage recurrent output. So that's why this kind of gates are known as forget gates. Okay, now based on that concept actually, okay, if you see the circuit diagram, okay, because we are using the concept of gating, that means there is something called as circuit diagrams will come like in electronics. So if you see that, you see just we have seen the shown you the circuit diagram only for that gate. So you see there is ht minus 1, then there is xt, right? So they are passed through a function f which is a sigmoid activation function which will give you some value between 0 to 1, that is z, right? Then there is phi, right? Then there is phi function which again takes the input ht minus 1, again xt is going to generate a proposal, not the direct but a tentative value. Then you see zt is multiplied directly with ht minus 1. Okay, so zt is directly multiplied with ht minus 1 which is added with 1 minus zt multiplied by ht bar. So you see this is 1 minus zt, this will give you 1 minus zt which will be multiplied by ht bar, again that will be added. So at the end you are going to get zt multiplied by ht minus 1 plus 1 minus zt multiplied by ht bar, and that will be the output ht. Now you see, for getting the ht, there is not just one path. Previously we had just one path. You can think of like previously we were just getting this output ht bar because there was no concept of gate. So you had just one path to ht minus 1 and xt. Okay, so previously you had just one path to ht minus 1, so there was a problem of basic gradient could occur if the network is too long. So now what will happen, because of this circuit diagram to this ht, now there are two paths. One path is in this direction, one path is in this direction also. Okay, there are multiple paths, you can go in this direction also, but the most important point is there is, you see there is one connection like this, directly there exists a connection like this, right? So when your zt is equal to 1, directly all these connections will be broken and you will have a path directly in this direction. Or you can think like if your zt is in the range of like higher ranges of near about to 1, then mostly this part of the neural network is going to be activated and your gradient is going to flow without any issues, right? So that is the concept behind gating. And based on that gating, actually in 1997, the long short-term memory, which is a very famous recurrent neural network actually proposed by Hocketeer and Stumdriver, 1997. It was proposed. It is an instant of previous gated recurrent unit with the following changes. Okay, so what are the changes? So they actually used the gating concept of recurrent neural networks that we discussed, but they did some changes. So the recurrent state is split into two parts. So what they did is that they actually changed the conventional way. What they did, they divided the recurrent state into two parts. One is CT and HT. So instead of HT, now you have two parts. One is that CT is the cell state. Okay, CT they call it as cell state, and there is HT, which is called as output state. Then they used three gates. One is the forget gate. FT selects the cell state information to erase. Okay, you can think of like the ZT, forget gate. So FT actually will select the cell state information. That means it will select from CT how much to forget, right? So that is why it is known as FT. Then an input gate IT selects the cell state information to update. So this IT will actually choose how much information I will take from the cell state to take it to the next stage. So you see the names itself actually give you the notations. FT stands for forget, right? So it helps you to forget the cell state information, how much information that you should forget from the cell state. IT will help you to find out how much cell state information that you should update. Okay, you can write UT also for update, but that's okay. IT for input, right? Generally they have proposed like this: forget gate, input gate. Then the output gate OT selects the cell state information to output. That means this OT will now be used to generate HT plus 1. So this OT will actually be used to generate the next stage output, that is the HT plus 1. Okay, so if you see the gating diagram or the circuit diagram of a LSTM mode, this is how it works. So you see, forget gate. Now forget gate, if you see FT, it again takes the input HT minus 1, the previous cell state, previous, in this case, previous output, right? Because we are representing HT as output state. Just remember, HT as output state and CT as the cell state. So FT, it will take the previous output state and the current input, right? XT and HT minus 1. Again, it will use a sigmoid activation function with the, of course, with weights and like we have used a logistic unit, right? So you see, it is taking HT minus 1 and XT, it will concatenate together. Then it will use a weight matrix with a BF, right, with a bias, of course, to generate FT. Okay, so you see the size of this FT, again, it's a vector of size similar to CT minus 1. Whatever this size CT minus 1 would have been taken, that would be the size of FT, because it will do a, so this dot with a circle, right, dot around a circle, a dot inside a circle is like per what do you say, per component multiplication. So if you have this one vector, this second vector, then it will multiply per element multiplication it is going to do. That means this FT depends on the number of elements in this vector CT minus 1. So you see, per element vector multiplication is going to happen over here. So this FT will generate a value between 0 to 1, and it will actually try to find out how much cell state to forget. That means your FT is equal to 0, then whole of the previous cell state will be omitted, right? So that is what is this FT is about. Then we can think of the other two gates, that is input gate IT, right? So IT, again, it takes the HT minus 1 and XT, and it will be passed through a sigmoid activation function. Again, it is going to get a value between 0 to 1, right? But the most important thing over here is the CT bar, or you can think of like the tentative value of the cell state, right? So tentative value of the cell state, you see, it is similar to what is this input gate, right? But with a 10 hyperbolic activation function, right? Again, when I am writing square bracket HT minus XT, means it is the concatenation of both HT minus XT, right? So the CT bar, or the tentative state, it will be actually generated from a 10 hyperbolic activation function, and it is going to generate a value between minus 1 to 1, because 10 hyperbolic can give you a value between minus 1 to 1. And that the researchers have done knowingly, because when you will do the plus over here, plus over here, when the value is near about to 1, then the cell state is going to actually increase, right? Because you are going towards 1. But if it is near about to minus 1, then the cell state is going to decrease. So they have done it knowingly to get the value either in the positive direction, even they can go in negative direction to decrease the cell state information. Okay, so that is why you see the 10 hyperbolic activation. So the CT bar is a 10 hyperbolic activation function which takes the input ht minus 1 and xt to generate your proposal CT bar, right? Now this IT will be multiplied with CT bar because as IT is known as the input gate. That means it will find out how much cell state information to actually take. You see, this FT is forget gate because it is forgetting from the previous input, right? Because if it is multiplied with the FT, depending on FT, it will take how much information we can actually forget. If FT is equal to 0, it will take no information from the previous cell state. But in this case, IT will actually see how much actually information you can take from this proposal, right? So that is why it is saying that how much. So if you see the definition of IT, it selects the cell state information to update, right? So IT, depending upon the IT value, actually it will take how much information to take it forward. Then that will be added with the CT minus 1. Okay. So you see your CT is now the current state cell state will be the addition of the CT minus 1. Sorry, FT multiplied by CT minus 1 and IT multiplied by CT bar. So if you see this equation, you see if FT equal to 0, then automatically you are forgetting the previous cell state, right? If your IT is equal to, let's say, 0, then you are actually not taking any of the input from the current cell state or the tentative cell state or proposal cell state, right? So that is why this IT we tell that is update state, right, or update gate, because it is updating or it is saying you how much you are going to update from the tentative proposal, right? So that's why it is known as the update gate. FT is known as the forget gate. Then comes the one more gate, that is OT, which is the output gate. Actually, it will help you to find out the output HT. See, till now we were discussing about the cell state CT, but as I told you, now your recurrent state is divided into two parts: output state and the cell state. So cell state we got it. Now how to get the output state? So for the output state, again we are going to use the OT. Again, it is similar to FT and IT, which will be passed through a sigmoid activation function to generate a value between 0 to 1. With the concatenation of HT minus 1 XT, it is going to generate OT, right? But what will happen? It will actually see. So if you see the convention of OT, it is saying that an output gate OT select the cell state information to output. That means from the CT, we need to take some part of CT to actually, what you can say, we can actually show it to the next state, right? So you see, if you see this diagram, we are using for this sigma. So this FT, IT or CT bar OT, we are not using CT minus 1 directly. We are using HT minus 1. That means we are using the HT value to actually generate, right, for the all these values of FT, IT, CT bar and OT. That means we need to take some part of CT that will be exposed to the next state, right? So that exposing state is the HT or the output state. So that means we are seeing how much out of this CT actually we can take HCT, right? So that is why you see, where is that next state, right? So OT is defined as again a 0 to 1 value, which will again the CT will be converted to the range of directly between -1 to 1, and from there on it will take some part of it. So OT will be a value between 0 to 1, of course. So it will take some part of it in the range of -1 to 1, whatever we have generated, to generate this HT. Okay, so what is happening now? Now you are exposing some part of the cell state to the next state, and this is going to be, this HT is now going to be used from the next stage, that is XT plus 1. So you see, if I replace this HT minus 1 with HT and XT with XT plus 1, so for generating FT, IT, CT bar or OT, we are using HT only, right? We are not using CT. That means some part of this CT is going to be exposed to the next state, right? So that is the concept of this long short-term memory. Okay. So by doing that, actually this task that we were doing, actually it gave you good results, and the LSTM actually performed far better than the other RNN, bi-directional RNN, stacked RNNs and all. Okay, then there are other concepts like gated recurrent units and all. With the interest of time, I'm not going to discuss that, but those who are actually interested, they can go through that, these gated recurrent units. Then there, like in case of neural networks, we get the problem of vanishing gradients. In case of recurrent neural networks, actually we can get the problem of exploding gradients. Gradients can go very high, right? So that also you can go through. And then there is a concept of orthogonal initialization. So like we do the Javier initialization, he initialization, and all those things in case of deep learning. In case of recurrent neural networks, actually we take the weights from a orthogonal matrix. Okay, so there is a concept called as orthogonal initialization in recurrent neural networks. That also you can see, and there's a nice concept how that it's actually generated with the help of Fibonacci series. Okay, so those who are very much interested, definitely they should look into that. Okay, so all these concepts are there. So with the interest of time, I'm going to skip all this. Right. So yeah, so any doubts you can ask, and I'm going to answer. Yeah, Dr. Deepak, are you available?
Sir, queries will be in the chat box.
Okay, let me see. So they are not asking questions directly.
Sir, their voice is muted.
Uh-huh. Okay. Why the function depends on input other than ht minus 1 as well? Why the function depends on input other than ht minus 1? So what I told you is that it is dependent on xt, the current state, or you can think like the current timestamp input, as well as the previous recurrent state output. So it depends upon both ht minus 1 and ht. Okay, so it depends on both ht minus 1 and xt. Okay, so why the function depends on input other than ht minus 1? I don't know what other than ht minus 1. I am not sure. So there is another question, sir. Can we use fusion of CNN and LSTM for training images for any application? Yes, definitely. That part I could not cover. So actually, you can use that. Okay, so you can use CNN and LSTM in combination, and you can actually generate image-based tasks. That can be done. Okay, so like in this case, this is one of the sequences you can see where what the sequences are used along with the CNNs and LSTMs are also used. Even you can come up with image sequences, and that can be done. In sequence synthesis, there is a question which is like it's saying that in sequence synthesis, the function is from RD to X. RD means I'm saying in general D-dimensional data I'm saying. So it's just some random data, D-dimensional data you are inputting and you are generating a sequence. So RD means it's a like R1, R2, you have Euclidean spaces, right? So D-dimensional Euclidean space, D-dimensional Euclidean space. That is what is meant by RD, right? So you can, if you very simple terms, you have D number of values in the domain of in the real value domain. Okay, so like 1, 2, 3, it's a R3. Okay, if you are thinking about 1, just a scalar, it's R1. If you have 2, like a point X and Y, 1, 2, it's a R2. Right, so RT means it's a D-dimensional Euclidean space point. Okay. So tell about the power set. So here power set is nothing but like we are generating the sequence of when you think about the power set, it is like you can think of like all the possibilities, right? So we are generating the sequence of length 1, sequence of length 2, sequence of length 3, up to sequence of length infinity. Okay, so that is the concept. I have written is infinity because in general, when you are thinking about English word dictionary, you have so many words and all, but it actually depends upon the number of words that you have, right? So based on that, actually you can have, even if you have 3 words, right? Let's say in your dictionary, you have 3 words, you can generate infinite sequence, long length sequence, right? So that is why all the combinations, that's what I was meant by these power sets, right? Anything else? Okay. Yeah. So with this, I think we will take a break now.
Sir, there is one more question
Yes.
in the chat.
Okay. Oh, there are
In below.
questions.
Sir, in below.
From which point? I'm not able to get it. 5.7, 5.9, 5.16.
Sir, the last chat from Sweta, like the last one.
Oh, the last one. Sir, if we want to process the video frames and RNNs get computationally costly, what could be the solution? Of course, it would be computational costly because the CNNs itself are very heavy and videos itself have so many. If you're thinking about videos, not images, so at a time you can actually pass number of frames as input. So that would be very costly. And the of course you have to see about like how this vanishing gradient problem and exploding gradient problem is going to be solved. So yes, as you have rightly pointed out, if you want to process video frames and RNNs, it can get computationally very high. But solution wise, like I gave you one example of like this gated recurrent units, right? Sorry, the gated concept, the LSTM concept, where they use the concept of gates to skip the connections. So by doing that, we can come over this problem of vanishing gradients. Then for coming over the problem of exploding gradients, there is a concept called as clipping that will help you to clip the weights to some certain value. Then there is a concept of, like I told you, orthogonal insulation, which will help you to not actually reach to vanishing gradient or exploding gradients. So that will help you to do orthogonal insulation. But having said that, if your number of layers keeps on increasing, definitely you are going to encounter lots of problems. So that comes to your design choices, what kind of designs you are going to do and all. Right. So it's a combination of many things that can be done based application to application. Let's say I am thinking about one application, maybe for that I using a very simplified model of a combination of CNN and RNN is going to work, but for some other application it might not work. So it comes to the concept of like how we choose our hyperparameters, how we choose our RNN architecture and CNN architecture. All these things will be combined together, and then it depends upon what kind of computational capacity that you are using, whether you are using a good GPU of size, again what is the size, what is the base size, what is the optimizer that you are going to use. There are so many things that are going to come, and always it will come to your application. That's it. Any other questions?
Okay, sir. I think there is no more questions.
Okay,
Okay, you
so
can take a 5 minutes break.
so we can start around 6:40. Yeah.
Okay, sir. Sir, you can turn your camera off.
Hello, you were saying something?
Yes, sir. You can turn your camera off.
Okay.